Okay, this is the 310 notes for Calculus 1. This section concentrates on our last type of important function for finding the derivatives of, the inverse trig function. So yes, there are derivatives of inverse trig functions. So what do we mean by that? Sine inverse of x, so sine inverse of x, often called arcsine in various places, in other textbooks and such. So when we need to find the derivatives of such functions, we get what you see here. So you'll see that this is a complete set of formulas that you will need to know for your exams. I know this is going to sound weird. I've been on this memorization kick for a while. I wouldn't say that it's entirely important that you memorize all of these. The most important one by a mile is the tangent inverse. That actually pops up a lot in Calculus 2 if you're going. So worth noting, if you want to memorize one and know one, it's that one for what you're going to be doing in the future if that's where you're going. But since this is an online class, then maybe not as much. So for the other ones, but what we're basically doing here is we're realizing again that these are all the base derivatives. So the derivative of sine inverse of x is going to be 1 over the square root of 1 minus x squared. Just like the derivative, the cosine inverse is just the negative of that. So you can see these two are identical except there's a negative sign here. By the way, the same thing happens in all of them between their functions and their co-functions, which we have already seen a pattern of in previous derivative rules. But some of these are weird. You'll see tangent is the most simple one, and the secant cosecant actually has an absolute value in it, of all things, with a radical, so it can get pretty crazy. But again, remember these are base function derivatives, which means the x's are placeholders for the inner functions, and to be clear, if you look at these, the bottom row, secant, cosecant, there's actually two placeholders for inner functions, here and here. So yeah, it's going to get pretty crazy, but that's essentially something that you have to remember when you're going through and doing the problems. This is a very short section because by now you should be able to do exactly what we're doing just with a different formula. So I'm going to go through, it looks like, I think 5 regular problems and then a 6th sort of all-together problem, and that'll be it for this section. Okay, so let's look at the sine inverse of 4x, its derivative. So again, it is a chain rule. Why? Because 4x is an inner function. It's not just x like here. It's 4x, which means we do have an inner function that we must manage. So the sine inverse is the outer function. So what is the derivative of the outer function? It's right here. It is 1 over the square root of 1 minus our inner function squared. Notice I didn't put just an x there. It would be wrong. That is just a placeholder for the inner function. Then I will have to multiply by the derivative of our inner function 4x. Well, we of course know that that is just 4. So if we're going to write the result, the 4 goes to the numerator and we get 4 over the square root of 1 minus. You can leave it as 4x squared, but realize that is also 16x squared. There's your derivative of the sine inverse of 4x. Okay, so let's just do a bunch of these. So cosine inverse of 2x plus 1. So clearly we have an outer and an inner function. Here's your inner function here, right? So we just have to follow the rule. Remember, it's the same exact derivative as sine, except with a negative in front of it. So if we're going to find dy dx, we have to do 1 over the negative 1 over the square root of 1 minus the inner function squared. So again, 1 over the square root of 1 minus the inner function squared. All right, there we go. And we have to multiply by the derivative of the inner function, which we know very well is 2. So somehow I changed the color, but it didn't change. Okay, now it did. All right, so what are we going to get? We're going to get that 2 is going to go to the numerator. Now it changes. 1 minus 2 plus x plus 1 squared. I would highly recommend not multiplying this out just because that is quite annoying to do. So that is going to be our derivative for our problem. Okay, moving on. What if we do this guy? So again, it looks like the outer function is the actual inverse trig function cotangent inverse. So cotangent inverse is right here. It is negative 1 over 1 plus the inner function squared. All right, times the derivative of the inner function. So we know that this is 12x cubed. That should be automatic at this point. And we just move that to the numerator. Wow, this is bugging out right now. Negative 12x cubed, 1 plus, and then again, if you want to change this, you can change the 3x fourth squared to 9x to the 8th, and you're going to get your derivative. Okay, up next, we have the secant inverse of x to the 7th. Okay, so dy dx. Outer function again is secant, so we return to our secant derivative, our base derivative, which is right here. So remember there are two placeholders this time, so we're going to get 1 over the absolute value of our inner function times the square root of, again, our inner function quantity squared minus 1 times the derivative of our inner function. Okay, so this is a little sloppy in here, so I'm just going to make it a little clearer. So x to the 7th in here. Okay, so note, since there are two x's, there are two placeholders for my inner function, so I had to write it twice within the derivative. So what do I have? This here is going to be 7x to the 6th, right? 6. So that means that I can move that to the numerator, 7x to the 6th. I have the absolute value of x to the 7th here. The square root, this is going to be x to the 14th minus 1. Okay, so believe it or not, there's a little bit of a change here, right? So if you look right now at x to the 6th and x to the 7th, that's actually simplifiable. So I can actually change that into 7, absolute value of x, x to the 14th minus 1, and this is your final answer. Okay, I can't move on without being very clear with a couple things here. So, or just one thing in particular, the absolute value. So, some students remember this, don't remember this. Just remember that you must leave an absolute value in a variable if the exponent is odd. Because if the exponent is odd, and we need to ensure that that part of the equation is positive. If the exponent is odd and we plug a number in for x that's negative, we're going to get a negative, and that's meant to make it positive. But if I got something like this, the purpose of the absolute value is pointless. Because no matter what I put in here, it's going to become positive with the even exponent, so the absolute value is not needed. So just remember the whole concept of odd exponents when it comes to this stuff. Okay, so let's switch up things a little bit and look at the next function. If you look at this, it's going to be y equals the sine inverse of x cubed with the entire quantity, the sine inverse quantity to the 4th power. Okay, this changes the dynamic of our problem because we now have an inner function in here and an outer function being our power to the 4th power, which means that the beginning of these problems have all been the same. Now this is going to change a little bit. Why? Because when we take dy dx, we need to use the power rule for our outer function. So what happens? 4 goes to the front, 4 sine inverse of x cubed. We deduct 1 from the exponent 3, and then we find the derivative of our inner function. Alright, so once we have this, then the first part stays as is, and we have to find this derivative. But you should see that this derivative is going to need another chain rule. So this is going to be one of those double chain rule problems. So what do we do? Well, the outer function now this time is the sine inverse. So what if we recall, the sine inverse is 1 over the square root of 1 minus x squared. So how does that work? We're going to get 1 over the square root of 1 minus our inner function squared times the derivative of our inner function, which we know that's a 3 here, is going to be 3x squared. Okay, so if we look at what we have left over, we have this is in the numerator, this is in the numerator, but this is in the denominator right here. So what does that look like? We're going to take this 3x squared, multiply by the 4, and get 12x squared. We're going to rewrite the sine inverse business, x cubed all cubed. And then we're going to do the square root of 1 minus x to the 6th in the denominator, which makes this the derivative of our function. So again, even though we're going on to a new topic, you must follow all the typical rules that you've seen before. You cannot move away from those when doing so. Okay, let's try another one. So let's say we did the cosecant inverse of e to the 2x. dy dx. So the cosecant inverse, similar to the secant inverse that we did up here, is going to have a crazy derivative, but it's going to be a negative sign in front of it. So this is the outer function again, and this is the inner. So we're going to do negative 1 over the absolute value of our inner function. It was x in the base function, but it's a placeholder. The square root of, again, e to the 2x, quantity squared, minus 1, times the derivative of our inner function, e to the 2x. All right, well this, we could use the chain rule, but we can use our shortcut, e to the kx derivative, to get 2e to the 2x, which means that we can go right to writing negative 2e to the 2x over the absolute value of e to the 2x, square root of, if we do, interestingly enough, I like doing this because I want to make sure everybody understands. So if I do e to the 2x squared, a lot of students will tell me that that is equal to e to the 4x squared. That is not the case in any way. That's not true. So e to the 2x to the 2x, you just do power to a power, and you get e to the 4x minus 1. Last thing, though, if you look at this quantity right now, we actually have something that can cancel out. This entire thing can go by, goodbye, and get negative 2 over just root e to the 4x minus 1, which is our derivative. Okay, so last problem. So in this section, I told you it'd be pretty quick. It says find the slope of the tangent line to the graph y equals tangent inverse of the natural log at the value x equals e. Okay, so this is one of those problems that probably give people a little bit of indigestion just looking at, but remember, I did bring back equation of the tangent line a couple sections ago. This is actually just looking for the slope, which means all we have to do is find the derivative and then plug in the value of x in order to determine the slope of the tangent line. So again, what do we need to do? We have to find the derivative, dy dx. So first step here. So dy dx, it looks like it's just the typical derivative. So we got tangent inverse. Well, tangent inverse, if we return to our problems here, get rid of all this. Gone. Tangent inverse is 1 over 1 plus x squared. It's the one I told you that will pop up a lot in Calc 2, so worth memorizing. So the derivative of the outer function is 1 over 1 plus our placeholder squared times the derivative of our inner function placeholder natural log of x. So once we get that, we actually know that this is a base derivative of just 1 over x, which is pretty neat, pretty easy. So if we want to go back and find a simplified version of that, it looks like we have nothing but 1 in the numerator, and then we have x, if we bring it to the front, 1 plus natural log of x squared as our derivative. Now this is not the answer to the problem. This is simply the slope of the tangent line at any point. We're looking for the slope itself at the point or at the value x equals e. So sometimes they do give you a point, so to speak, for this, but they didn't for this problem. They just said, hey, what is happening at x equals z? So what do we have to do? We have to plug in e into all of our values of x. Okay, this does seem like it's going to be stressful, but believe it or not, it's not going to be stressful. Why? Well, first of all, e, we don't need decimals here. We can just do exacts. This is not stressful. Why? Because this is an identity. So the natural log of e is equal to 1. Why is that? Because the natural log is the log base e of e, and that is always equal to 1. So we can replace this number right here with 1. So let me write it the way I usually write it. So this here is 1. So if we do that, look what happens. We get 1 plus 1 squared is 2. So all we are left with is 1 over 2e. So believe it or not, that is the slope of this tangent line to this graph at the value x is equal to e. Note, I didn't ask you to find the equation of the tangent line. You probably know why, because it looked absolutely awful. But if I had, then you would have to plug e into here, get the tangent inverse of 1, find that value. Hopefully most of you are like going through your head right now and realizing what that is, pi over 4, but you're going to end up plugging that into, y minus y1, blah, 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 in order to find the equation. It'll just look horrible because it's going to have 1 over 2e, it'll have e, it'll have pi over 4, it'll have a bunch of values in there that you'll be using, but 1 over 2e is all I'm looking for in this problem.